Hi, Nitin sir. I've made you the host, so you can start the session in a bit.
Okay, thank you.
Thanks. Bye.
Okay, good evening. We'll start off with today's session. Okay, today's session is the continuation of the previous thing in organic chemistry, where here we are mostly dealing with the reactions and of non-metals and extractions of metals. Basically, when we try to term this is something which is related to metallurgy. A lot of theory, direct questions. How much you remember, that much you can answer. Okay. What will be important in all this? I'll tell you that so that you can just brush up your things when you're revising it. You can know that what is you're supposed to read. Okay, starting with when you're talking about the periodic table, as we know that we have group 1 and then we group 2, then we have group 3 to group 12. Further this, we have again group 13, 14, 15, 16, 17, and 18. So all these things, these two are metals. There's no doubt about this. These are metals. This again is metals, which is the name only is there for them is transition metal. This is transition metals. Still up to here also, from here we have the first member which we count as metalloid as well, but aluminum behaves as a metal. Lightweight metal, which is very well helpful because it is lightweighted and it have all the properties of metal. It was the time when it was discovered, it was a boon for the aircraft industry because it was previously iron made things were very heavy, but aluminum substituted it. Now, when I talk about group 14, that is carbon, silicon, all this all are having properties of what covalent bonding. So these are moreover like they don't show that much good metallic character. From here, there will be some character of metals as well as non-metals. We say it as semi-metals or metalloid. Group 15 onwards, we have huge change where we start getting non-metals from here, non-metals. And group 18, as we know, this is unreactive, this is a noble gas. So at present, you don't have to know anything about this. Only particular noble gas which compounds are known or which is supposed to be read by you is xenon. Xenon is the thing which have compound with electronegative elements like oxygen and chlorine. Except that what you have to study in that there's nothing, no other thing you're supposed to find out. Okay, that's the first thing. Now when I'm talking about metals, how I decided this is metal because this have plus valencies, +1, +2, and here will start going, so they'll get negative valency. Based on that, we decided this. Extraction for this metals or transition metals is very much important to be read. So we are supposed to be reading the zinc, copper, iron extractions or all this. These all are transition metals, very important to the industry. Why we are not, even though this is metals, but we are not talking about their extraction. They are very reactive. So they are very reactive. It's hard for them to keep them in separated form. So they are very reactive. So we can't keep them in a form where we are not we are able to combine it. So the span of time where they'll stay, they'll not react or they'll not combine with something and they'll stay as a single element. It's very less. So that's why, but though they are very reactive, we use them for certain reactions where we have to displace something which comes under them in your activity series. If you know activity series starts from lithium, then you have sodium, potassium, everything is there which are group 1. Then magnesium is there, calcium, all these things are coming at top of the activity series. So they're very reactive. So normally transition metal, and as further we'll move, we are supposed to check elements related to this. So from here, we are supposed to know about ammonia. We'll be reading about ammonia. From here, for sulfur, we are going to read about SO2 and we are going to read about H2S. And then I'm talking about, from here also, we are reading extraction of sodium 1. Okay. Sometimes you'll see that Na is being used as if you're reading organic reaction, Na with dry ether. So Na, again, I said no, it will be used for displacing something which is lesser reactive to that. And we can't take lithium because it is very smaller in size and it doesn't form, it's mostly try to form ionic bonds. Okay, so now this is from this chapter. This is halogen. From halogen, we are supposed to talk about Cl2. We are supposed to talk about HCl. Now, when I'm talking about oxides or hydroxide or carbonates, oxides will be what? Normally, if you're talking about this thing, oxides of this group will be what? This will be formed in, this will be M2O. Here they'll form MO. Why? Because valency of O is 2, -2, and here this is +1. So from the crisscross method, I'll get oxides of this form. Or if I'm talking about metal hydroxide formula will be in this form, MOH. Okay, if I'm talking, so this is hydroxide. If I'm talking about carbonates, so I'll get it in metal. Some metal will be there with that carbonate will be there. Depending on their valency, the compound will be formed. Now, so if I'm talking about Na, the group 1, so it will form what? It will form Na2CO3. Or if I'm talking about first group hydroxide, NaOH. So all we say why NaOH is very, this is very strong alkali. This is a very strong base. Why this is very strong base? Because it's forming. We have Na, which is there from the group 1. It will have been taken from NaCl, which is a very. So this will be what? This will be very reactive, and this is what? This is a salt formed because it will be from the strong base we take Na, and like Cl is taken from some strong acid. So when strong acid and strong base combine, we form a salt, which is a neutral salt. This is why NaCl is. So we have to basically deal about whatever metals are there, how their extraction happens, what is there in electrolysis, what is types of steel, and how the steel manufacturing is there. All that is be dealt in this chapter. Okay. So starting with the first thing, we have to start with the first thing we'll be reading is this extraction of metal. Normally, see, we talk about the theoretical part, which can be written, we can write, but this have a lot of theory, which in which you have to just mark down those things which are very important to you. So, extraction of sodium, sodium being very reactive. First one, you should know sodium is what group one. What will be its valency? It will be what? 1s2, 2s2, 2p6, 3s1. So this 3s1. So this is the one electron which is there. Now, what is NaCl? Because there is a lot of problems with NaCl from other methods. That's why they're trying to use what we are trying to do this method using extraction. This is known as Downs method. Okay, this is known as Downs method. This one is Downs method. So what we are doing in Downs method is basically NaCl is mixed with C. Now, what is important for you is, see, the theory is written to explain you. Now, what you will be doing is, now, see, I know that what is their mix. So I'm seeing what is NaCl is being mixed with CaCl2. What is the ratio? 2:3. First thing, what is important, and this 2:3 ratio is by mass. So there is a lot of difference when I'm talking about by mass and by volume. Lot of differences there. When I'm talking about by mass, or if I'm talking about by volume, you have to show this. So NaCl plus is mixed with CaCl2 in the ratio of 2:3 by mass. Okay, and this is being reduced. Temperature here, what we are using temperature is 600 degrees Celsius. Now, except this, all these things, whatever is there, electrodes are present. The electrodes, what we have is, we have graphite. You can see here we have graphite anode and iron cathode. See, graphite anode is why it is used somewhere, because this is somewhere in like inert, we say. Somewhere it behaves like an inert and electrode. So graphite anode is being used. Now, what is there? The cell consists of one inlet through which the electrolyte is poured into the cell. What is the electrolyte here? This is what is the electrolyte. Electrolyte is being poured from here, and this. So now you see this all. So either you use NaCl plus KCl plus Kf, or we use NaCl plus CaCl2. It is being fed from this in the solution. Now what happens? Electricity is passed through it. So then the electricity is passed into the electrodes, which initiates the electrolysis. The chlorine gas is collected at anode, okay, first, and the sodium metal is extracted at cathode. You need to know this, where it is what. So we have reactions here. At anode, chlorine is there, and at cathode, Na is there. Okay. Sodium having low density, then its salt floats and can be easily collected over kerosene. We are using over kerosene because kerosene will not. See, kerosene makes NaCl. If you see reactive metal like this is kept into NaCl, you'll be reading from many years that we use very reactive metals like sodium and all are kept into kerosene because they are very reactive towards air. They are very reactive towards water. Now, so this is the full story. What is important for you? Electrolyte used between this is NaCl plus CaCl2 into 2:3 will be ratio by mass. Temperature will be 600 degrees Celsius. At anode, chlorine gas is being formed, and at cathode, sodium is being extracted. Why sodium is being extracted? Because it's a low density. It's a very low density, and because of that, it will float and it will be collected over kerosene. Only this thing is what is important in this. Explanation wise, everything is there. You can see graphite anode is there. We have iron box lined with fire bricks. This will, it's going to behave as cathode. Now we have wire gauge sodium. From here, sodium will, because if I'm talking about here in the solution, now what will be there in solution? Na plus is there. So Na plus is losing, it will be losing one electron every time to convert itself. So this is what is being converted to Na. So from where this electron will be coming? This electron will be coming from the anode. So balance the charges, we have cathode and anode. So again, same thing, I just suggest you what you are supposed to know. Electrolytes are which one? It is just NaCl plus CaCl2 in the ratio of 2:3 by mass, one thing, or you can just take it as NaCl plus KCl plus Kf. Anything is fine, or both of this can be used as electrolyte, but the ratio here will be 2:3. This is what your syllabus suggests. So NaCl plus CaCl2 2:3 by mass. The working temperature is 600 degrees Celsius. In the exam, they can give you it in the terms of Kelvin. So just add 273 to that. So it will become 873 Kelvin. So that is, you have to see the options carefully that they're giving you somewhere. Maybe they'll give you something around 873. They'll give you 893. They can get 883. So 600 plus 273. What are the anodes? So electrodes here are graphite is anode, iron is cathode, chlorine is being extracted at anode, and sodium is being extracted at cathode. What I was doing this was the thing which we intended for. We wanted sodium. The process name is Downs process. This is what we're supposed to know from this. Okay. Now next, what is there is you have to form manufacturing of caustic soda. Caustic soda is nothing but sodium hydroxide. Okay, sodium hydroxide. A sodium hydroxide, so you have two methods of doing is one is NaCl. From NaCl, electrolysis method is there using which we can have it. But for your syllabus, what is there is they want the things which is initiated using sodium carbonate. So by using sodium carbonate as starting material, we have two processes which we can use. One is causticization process, which is known as Gaussige's process. So what is there is Na2CO3 is reacting with CaOH whole 2. Okay, CaOH whole 2 is also known as slaked lime. Okay, this forms calcium carbonate and 2 NaOH. So this is what I was intending for. Okay, the temperature here is maintained at 80 to 90 degrees Celsius by blowing steam. Okay, caustic soda solution is drained out of and evaporated to dryness when flakes of caustic sodas are obtained. The most suitable concentration of sodium carbonate taken, what is the sodium carbonate we are taking in the process is 15 to 20%. 15 by 20% is purity we are talking about. In this total, I'm trying to react Na2CO3 with CaOH. I am just intending that 15 to 20% in that solution, I should have Na2CO3. Caustic soda produced by this method is not that pure. It contains calcium carbonate, sodium carbonate, and calcium hydroxide as impurities. Okay, so this is what is there. What is important next is Loic process is there. So what is important in this again? See what is important. That's what you're supposed to focus on. Don't see that sir, this much theory is there. Reaction is important. First thing, temperature maintained is 80 to 90 degrees Celsius. What is the sodium carbonate? Take concentration of sodium carbonate is 15 to 20%. That is not this much pure. That's what you have to know. So what is supposed to be the first method is Gaussige's process. Gaussige's process reaction is Na2CO3 plus CaOH whole twice. Is this basically is this Na2. This is sodium carbonate plus CaOH whole twice. This is slaked lime plus. So this forms what? This is forming CaCO3 plus 2 times NaOH. Okay, if I want to see the reaction, you can see that Na2CO3 will break as what? It will break as 2Na plus CO3 2 minus. It will break in this CaOH. If you find out, CaOH will break as what? Ca2 plus 2OH minus. Now negative of this will go to the positive of this, and negative of this, positive of this. So if you talk, so this is why this gives you what product? This together give you CaCO3 and negative positive to this will give you 2NaOH. So this is why we are getting the product of this. So this is the reaction, and then the temperature is 80 to 90 degrees Celsius. Keeping in mind, they might give you the data in the terms of Kelvin. For whatever is obtained is what we are trying to obtain is caustic soda. Concentration of sodium carbonate 15 to 20%. That means in this total solution, 15 to 20% will be sodium carbonate. First method, and I'm talking about manufacture of caustic soda. Next is the second one is Loic's process. Loic's process is more efficient. Okay, this gives you much pure. When I'm talking about caustic soda, reaction against Na2CO3. Okay, so Na2CO3 plus Fe2O3 forms. I just try to break this. It will be 2Na plus. Generally, when I'm talking about inorganic reactions, most will be like this. Organic have different logic. Now we have Fe2O3. If you know here, this is there. So I have to see now. Oxygen here is what? -6. -2 times this is 6. So this will be +3. Now for iron, what is there? Iron we have possibility of +2, +3. More. Whichever is more, that ends with 8. Whichever is less ends with us. Okay. So this is how, so we will try to remember because we have variable valences there. So here, because it is giving +3, so it will break as what? Fe +3. And here, then again, I have O2, so O2 minus, because to balance that, I have +3, here I have -2 charge. Okay. So now again, same thing, positive of this to negative of this. You can see that I have what 2 NaFeO2 is going to join here, and CO3, this 2 again, this is unstable. So this break as CO2, and this CO2 combines with your, this stays in one product, and Na plus Fe with this one O will combine to this position. So any, just to remember this, if you have what you have variable valency, the lesser one is us, more one is ik. This is the two reactions which are important here. And after these two reactions, we have the further thing which is important for you is in this process is this thing. What is the temperature maintained here is the same amount of temperature is being maintained here as well. So reaction wise, you have to see that this, they can give you the reaction is like which among this is the process of manufacture of Na2O, process of manufacturing of NaOH using Na2CO3. So this one is Loics method. This is one. Next one is Gaussian. One more is there when we can use NaCl as starting material for your syllabus. That is not there. That is using electrolysis. Okay, next we have, next is extraction of copper, or copper again, number is how much? Copper value is 29. Okay, again d block element, they are very important metals. So what we do is in this is being taken from copper pyrite Fe2s, copper pyrites as Cu2s, like this. Iron pyrites will be there, like that. You have copper pyrites Cu2s, CuFeS2. Copper pyrite will be what? CuFeS2. This is copper pyrite, and copper is extracted from this ore. Okay, the principal role of copper is copper pyrite. From this we are trying to extract the copper. The steps are what? This all is what? This all are metallurgy steps. So first what we are doing crushing and concentration. What we do crushing, we will try to break it into the smaller pieces. Concentration is we try to clean it off. Okay, so the ore is obtained from the mines, are broken down into small piece by jaw crusher and then pulverized. Pulverized means high pressure will be high pressure water, high pressure liquid will be passed through it so that it can separate the, if you have some lighter weight impurities in there. Now because we have sulfide ore, when we have sulfide ore, for that we use fourth flotation methods. What I am taking is important, that's why I'm marking it here. So what is the first thing? You have copper pyrite is the ore for it. First thing. Second thing, after this you find out the ore is sulfides. For self cleaning or for cleaning or concentration of sulfide ore, we use the process as fourth flotation method. Wherever sulfur is there, you see again group 16. We have read in periodicity, group 16s are normally ore forming. So ore forming group is that. Okay. Now what we do is pulverized ore is kept in water containing pine oil, and the mixture is agitated. Agitated means like this, we try to put surf in the bucket in the water, and we try to mix with our hand. That is basically we are giving agitation. Okay, passing through compressed air. Ore forms froth with pine oil and comes to the surface and skimmed off while impurities are left in the water. So ore will be taken out from here. Okay, and impurities, this is gangue, which is mixture of impurities. Fine. So this is how we, first step is this. After we are done with the first step, next step is roasting. The concentrated ore is heated in excess supply of air. Excess supplies of air on the hearth of a liberatory furnace below its melting point. M is missed here. Below its melting point. So it is not, we can't allow it to melt, because if you melt it, it will go to the next other form. So the different changes during the roasting will be, the first is what? Moisture and volatile impurities will be driven out. Non-metallic impurities like sulfur, phosphorus, arsenic, etc. are removed as their oxide. This is what roasting does. If you talk about roasting, or if you talk about calcination, in both the cases, what we do is separating out the metals or non-metals impurities. It will be difficult. So what we do for non-metals, we try to combine them with oxygen, and we try to separate them in the form of their oxide. Okay, so this is the example, but this is not important. The next step is this. So you have written also a major reaction. So we have copper pyrites here. In presence of oxygen, we are trying to dissociate into, this is Cu2s, 2Fes plus S. This is the major reaction. Small amount of metal sulfides are oxidized to oxides also. So Fes is being oxidized. Okay. So next is we are going to smelting. The smelting is the roasted ore, coke, and silica is charged with a water jacket. 1 minute. So this is the reaction which we were reading. Now further, when we are talking about after this major reaction, next is when I'm talking about the smelting, what happens is the roasted ore we are trying to combine with oxygen, Fes and SiO2. This forms ferrous sulfate, silicate. This formula you remember. Silicate is basically SiO3. We can have SiO2, SiO3, SiO4. All these are silicates only. Silicates is particularly, it is a compound which has different structure. It has somewhere here in this case, we have silicon, O and O present here. So like this, somewhere like this structure will be there for this. So this structure and all you don't have to read at present. This is, you have to remember that this is ferrous silicate. As long as Fe is present in the mixture, CO2O can't be formed as copper. Okay, because why? Because iron is there, which have more affinity. This is Fes. Fes is present, then you can't separate out copper. So what we do is, why? Because it have higher affinity for sulfur than oxygen. So they'll start combining again. Okay. So we can't separate it in the form of oxide. So what we do is in molten state, Fes and CO2 plus, this is known as copper matte. Copper melt, it's written here. This together, this two is known as what? Copper. Or many people write it as copper matte also. Many textbooks, so don't get confused with this. Okay. Fes, Cu2 plus together. This mixture, the lower end of the blast furnace has two openings for slag and copper metal. So one from one place we have tap hole. So from here this is molten slag is obtained, and from here we are using copper metal. So this is what is the arrangement. You don't have to again remember all the arrangements, obviously. What you have to, what is the formula for copper metal? So you should know Fes plus Cu2s. Okay. So this is what is important in this. In this, whatever we are marking important items, because see, for anyone, it's not about you, it's not about others. For anyone, reading a lot of theory is not easy. Reading is okay still, but remembering and keeping it in the mind is not easy. Okay, so now the molten matte. See here it is written as matte. This is Cu2s. Copper is there, and then copper is there. Then we have what? Okay, Fes and Cu. This is there together. So now what we do is Fes we try to react with oxygen to find it as FeO. Now what here we are trying to convert it into FeSiO3. This is what is the slag obtained. Now the slag is removed and air is passed. This air oxidized Cu2 plus partially to Cu2O. Now I am able to separate them. Correct. Now I am able to separate them. What I am able to separate now? I'm able to separate them when I'm trying to go to the besmerization. Besmerization is basically, this is what is the Bessemer cells. It's not like some other reaction. Besmerization we are trying to do. We are trying to put it in the Bessemer. Okay. Now what we are doing, Fes is being oxidized to Fes. Wherever I'm trying to first here oxidation of Fes happen. It is oxidized to FeO. Wherever addition of oxygen is there, that is what? That is oxidation. So here oxidation happens, it forms 2FeO. Now after that FeO plus SiO2, it is forming FeSiO3. This is again ferrous silicate. So this is in the form of slag. Once I'm trying to now see, I'm able to obtain Cu2O here now. Now this Cu2O, which then reduces remaining Cu2 plus in the metallic copper. So what is happening here is now CuS with oxygen is getting oxidized to Cu2O. Once I'm getting Cu2O, this Cu2O further reacting with Cu2S to separate copper. So this is what I was intending for. Previously it was not easy. Why? Because the FES is also present in the mixture. So what I did, I oxidized FES because oxidation oxygen will first react with Fe. Whenever you're trying to give oxygen, first it will, Fe being more reactive than copper, it will first form the compound with Fe, so it will oxidize to FeO, but it is not easy to separate FeO. It is still reacted with SiO2. This SiO2 forms ferrous silicate. In the form of slag, it is taken out. So what is left out now is Cu2S. During this reaction where oxygen is being supplied, partially Cu2S is already being converted to Cu2O. Then further it is being reduced using Cu2 plus. So now Cu2O, which is being prepared here, is using Cu2 plus, which was fully reduced to copper. So that's why the reaction is highly exothermic. Highly exothermic means what? Delta H will be negative. The heat of enthalpy will be negative. Okay, so negative heat enthalpy will be there, like combustion, and copper is obtained in molten state. Obviously this much heat is there, so molten state means it will be basically lava kind of thing. So during solidification, SO2 will escape and this will be allowed to cool. So SO2 being a gas, it will escape out from the blister of the surface of the metal here. From here SO2 will come out, and the variety of copper containing about 2% of impurity is blister copper. So what is blister copper? Blister copper is that thing which contains 2% of impurity. You should know this also. Okay, so what you're supposed to know on this page, this is not important, so you're not getting into this. This reaction is important. If somebody is reading, we have to choose this. They'll give this is first priority. This is how the copper is separated. This reaction is to separate iron, because if iron is not separated, it will every time react with oxygen to form further iron oxide. So instead of forming that, we react it and we try to separate it in the form of slag. So what is the reaction? It's highly exothermic. It's too much of heat is being taken out. Now this is the copper is found in molten state. The copper which is obtained here is 2% of impurity it contains, and that is known as blister copper. So this is what is important here. Next, so when I'm trying to do refining of the copper, so blister copper, which consists 2% of impurities, blister which is containing 2% of impurities, that is silver, gold, zinc, nickel, all this you can see is D block elements. So it is mostly purified by electrolytic method. Electrolytic method is what? Electricity is being passed through it. So what we do is a block of impure copper is anode. So a block of impure copper is anode and a strip of pure copper is cathode, while a solution of copper sulfate is, which is containing dilute H2SO4, is electrolyte. So what is electrolyte here? Electrolyte is copper sulfate. Electrolyte is copper sulfate. Sir, please provide PDF note. Yeah, I have informed them about this. I know you need a PDF for this. Correct. So copper sulfate plus dilute H2SO4 is there. So this dilute H2SO4, this is together. This is our electrolyte. Someone is unmute. Please mute yourself. Okay. So electrolyte, this is CuSO4 plus dilute H2SO4. Now what is anode? Anode is your impure copper. Anode is impure copper. Anode is impure copper. And when I'm talking about cathode will be strip. They're taking a strip of this very thin metal, very thin. Okay, so now you can see what from this impure copper. This is basically is melting, and the pure copper is depositing on this. Okay, so this is what is there. CuSO4 breaks down into Cu2 plus and SO4 2 minus. Okay, at cathode, this is what is there. At anode, this is there. So what I'm trying to see, We are on passing current, impure copper dissolved, and equivalent amount of pure copper is deposited at cathode. So where the pure copper is being deposited, it is at cathode. Okay, C for C, copper for cathode. So this is easy to, pure copper is deposited at cathode. Okay, 2% of impurity of that copper is known as what? Blister copper. That is what is important. So here this is, and impurities are collected below anode as anode mud. Not important. What is important is blister copper is important. It contains 2% of impurities, which contains silver, gold, zinc, nickel, all these D block elements. So what we do, we use electrolytic method. We try to pass out electricity. In that, what we use electrolyte, which is a mixture of copper sulfate and dilute H2SO4. Anode, what we have kept impure copper. Cathode, what we have kept pure copper. When electricity is passed through, as the reactions move on, pure copper is deposited at cathode. Next, this is a compound which is made up of copper, which many times you would have read it as copper sulfate or 5H2O. It normally exists in hydrated form, that is blue vitriol. Blue vitriol is normally you find it out. This is known as what? This is known as water of crystallization. This one is water of crystallization. So normally it will form in this only, water of crystallization. This is water of crystallization. Blue vitriol is what? CuSO4. Normally, this is in blue color, crystal form. That's why we write it as blue vitriol. In laboratory, it is prepared by dissolving cupric oxide or cupric hydroxide. Now, what I'm writing is cupric. All three I've given. Cupric again, copper is there. Copper oxide +2 state. That's why I'm writing cupric. Copper also have +1 state. That is known as cuprous, which will be less. Okay, which will be less. According to that, how I have remembered, if you know variable valency, then in Hindi there is a word which ends with adhik. So adhik, if you remember, adhik ends, it sounds with ik. Adhik in Hindi, basically English meaning of that is more. So more, for that we have ik. If you know variable valency, there is 6 to 7 variable valency when we talk about metallurgy. So if you know that, if you have, like if I'm talking about iron, just now I said you +2 and +3, which is more, this is more. So this will end with ik. So I'll just write it as ferric. Why I'm writing ferric? Because ferric, if I'm talking about the name of iron, it is ferrum, like Latin name. If I'm talking about silver, it is argentum. Talking about gold, it is aurum. So based on that, we write it as AU1, AO, like based on that, we try to write. Okay. Okay. So anyway, this is there blue. So copper oxide is reacting with H2SO4. It forms copper sulfate. What is the form of H2SO4? I'm using dilute. Doesn't need that much concentrated. Liberates H2O. Here also CSO4 liberates H2O. CSO4 liberates H2O. This is again good because this will be escaping out in the form of, all the reactions are same. We have the formation. If you try to react with oxide, hydroxide, or carbonate with H2SO4, they'll form CuSO4, H2O, H2O will come out. In this one, extra product is there, that is CO2. This is important. Okay, the next method which we are supposed to read is about extraction of zinc. So concentration, how we are doing extraction of zinc, we are having concentrate. We are trying to find out extraction from here. We are trying to get it from zinc blende. We are trying to do extraction of this by using zinc blende. Zinc blende is this, zinc sulfide. The name for this is zinc blende. So you just remember this, zinc blende is this name. We are using again flotation process here because we have sulfide here as a ore. So same thing what you studied there will come here. The pulverized ore is kept in a large tank containing water and pine all there. Also, if you remember, pine all is there. The mixture was agitated. So here also we are agitating the mixture. And ore forms on froth. Froth is means on the top you'll find out the slags kind of thing, jhag kind of thing. That is froth, and it comes on the surface while impurities are left in the water. So same froth flotation method why you are using, because sulfide is the ore. So basically what we are doing, crushing and we are trying to concentrate it. So here zinc blend is not in that much, the shape is not that big, so we need to crush it. So we are directly doing concentration, which will separate the basic impurities. After that, we are going roasting. Sulfide is there, roasting will happen. Roasting is done in excess supply. When we are talking about calcination, it is done in limited supply of oxygen. It is done above 900 degrees Celsius. Okay, during roasting, zinc sulfide is converted to zinc oxide. So this is what is roasting. Roasting or calcination, again, roasting oxygen, we are saying that we are supplying excess supply of air. So obviously it will combine and form oxide. Now a small amount of zinc sulfide may be oxidized to ZnSO4, but this will happen only when the temperature crosses above 9,000 degrees Celsius. So ZnS2O2 forms ZnSO4. This is only possible. This reaction is basically written if ZnSO4 is there above, if its temperature is greater than 900 degrees Celsius, 9,000. Okay, so this all have been wrong. It is not 900 degrees Celsius. Sorry, it will be not 9,000. It will be 900 degrees Celsius. Okay. Based on that, we are trying to find out. We'll get zinc oxide, sulfur dioxide, and O2. Okay. So this is not important. What is the first thing you have to react? So remember, is zinc sulfide, when presence of oxygen, forms ZnOSO2. This is the first thing. Next, so see, this much story is there, but what you have to remember is Froth flotation method is used. Why it is used? The ore is zinc blended, that is ZnS. ZnS sulfide ore it contains. So sulfide ore, this method is what? Froth flotation method. After that, roasting above this temperature, we are trying to do it, and above this temperature, this will be 900 degrees Celsius. Okay, this will be not 9,000. This is, I think, degrees Celsius, they have written it as 9,000. This is 900 degrees Celsius everywhere. Okay, so 900 degrees Celsius, above this will happen. It will form zinc oxide. Okay, next. So once I got what I got after roasting, what I got is zinc oxide I got. So now zinc oxide, I'm trying to use carbon here. This carbon reduce it is to zinc and carbon monoxide. Now the reduction is done in the vertical retort. This will be a vertical retort. If this process roasted or mixed with coke in the ratio of 2:1 and small briquettes are made. Small briquettes are basically, you take this mixture and you try to find coal mixture form in the powdered form. Okay, briquettes are basically in powdered form mixture of coal. Okay. So these briquettes are fed into vertical retort furnace from charging door. The retort heated externally by burning produce gas. This is not W, it has to be CON2. Okay. So this CON2. About 1400 degrees Celsius. This will be 1400 degrees Celsius. Okay. So the vapor of zinc came in the condenser where the condensers to give molten zinc. This molten zinc is known as spalter zinc. Spalter zinc. This is still impure. There, which was there, copper, blister copper. Here, zinc is what? Spalter zinc. Okay, so every time before they'll be getting fully pure form, there will be some impure form. So now purification of zinc spalter is why it contains Pb, Cd, arsenic, etc. This is arsenic, cadmium, lead, all that has impurity. So impure zinc can now be purified by following two methods. One is by fractional distillation. Obviously, what we are getting here is 99% pure. Okay, so boiling point of Pb are higher than zinc, while that of cadmium, arsenic are lower than that of zinc. So when distillation is carried out around 100 degrees, this is 1000 degrees Celsius, zinc, cadmium, arsenic, etc. distill off lead and iron. What is there? 800 degrees Celsius. This will be distilling off. So sample here, whatever will be containing is. If you remember, fractional distillation is basically done in the process, which is because of the difference of melting point or boiling. Now, what is electrolysis here? Electrolysis, again, say you'll try to find out electricity. What you'll use here is pure zinc rod will be used as cathode, copper as cathode, pure copper as cathode, pure. So metal will be always at cathode, while a block of impure zinc will be at anode. Okay, mixture of ZnSO4 with dilute H2SO4. There, the mixture was what? CuSO4 plus. So if you see what is common here is they're trying to use, or normally when I talk about electrolysis, they use the electrolyte, the salt of the same particular metal which we are trying to extract from. They're also in the final. So blister copper, final thing what we did, we have taken pure copper at cathode. Here pure copper again is zinc, which is taken as cathode. Then again impure as anode. They're also impure. There it was copper sulfate plus dilute H2SO4. Here it is copper sulfate plus dilute H2SO4. You don't have to remember see, this impurities and all. While you can put a reading, but you don't have to separately write that this is what is present as impurity. This is what is present as this is what is having higher melting point. Now there, this point we are saying PB is there. Okay, this is having higher melting point. Now I'm talking about cadmium arsenic. This have 1000 degrees. So all this temperature data exactly you don't have to remember. What is what is obtained by fraction distillation is 99% pure. Here also whatever you obtain is 99%. Okay. Which is more better? Obviously, this will be more costly compared to this. So, whichever, depending on the situation, so which is better? Obviously, electrolysis faster. Even though it is what is disadvantage, it is more costly. But don't expect all that question for you now. That advantage and disadvantage they're asking, they're not going to be that good to you. Okay, galvanization is basically what you are doing is things like iron or metals to avoid rusting. We try to put a layer on these things of zinc. Okay, so galvanization is the process of applying a protective zinc coating on iron or steel to prevent rusting. Okay, it can be done by two methods: hot dipping method and electrolytic deposition. In hot dip process, what we do is cleaned iron or steel, usually in the sheet form, is passed through a electric flux is there, such as zinc ammonium chloride. We try to pass it through zinc ammonium chloride and guide it through a bath of molten zinc. So this zinc will be present in the lava zinc form, and this will be allowed to pass through it. In wire galvanizing, the wire is drawn through successive pickling. Pickling, annealing, and washing operation is pickling basically is cleaning. Annealing is application of zinc on that, and then after that you're cleaning it so that there will be no impurity which is stick on that. It is then dried before passing into the galvanizing pan and is drawn out through wipers of charcoal, coke, and sand or asbestos. This all are what? These all are insulators. So that by the time it comes out of this, it will be fully cool and you can take it out. Okay, fine. Which is better is a hot dip process. Okay, hot dipping is better than electrolytic deposition when I'm talking about galvanization. So you should remember hot dipping. Electrolytic deposition is not there, it is not required for you. But I have just to compare, I have written it here. So what you have to do is you need to do hot dipping process. What is being done here is first clean as a flux. You can use other material as well, but here we have taken example of zinc ammonium chloride. Zinc ammonium is NH4Cl, zinc is Zn, and it is guided to a molten zinc. Molten zinc, it is in lava form, high temperature melted zinc. And then what we are doing, we have successive pickling, annealing, and washing operation. What is pickling, what is annealing, and washing operation? They're not asking you. Pickling is what basically you're trying to clean the surface of the metal. It can be iron or steel. Annealing is you're applying, you're trying to clean that sulfur by applying metals through it. You're trying to apply the layer of zinc over it, and then you're trying to clean it. Once one thin layer of zinc is applied, then this is taken into the galvanizing pan, and then it is drawn out through wipers of charcoal, coke, sand, or asbestos. Anyone can be used. Why? They are insulator, so that the temperature by the time it comes out is okay. Okay, when this all is the intermetallic compounds of iron and zinc are formed on the surface of steel or iron being treated, whichever you are trying to take. So finally divided zinc below the melting point of the zinc. In another, molten zinc is applied. Okay, we can, if it is not that much important or it is not that much big surface area, what we use, we take molten zinc and fine spray to the surface of the cleaned iron and steel. This zinc adheres, it sticks tightly to the surface. So this is also is possible. For galvanization, what is important for you? Two processes there: hot dipping, electrolytic deposition. Hot dipping is what important for you. In galvanization definition, you should know what is the definition: the process of applying a protective zinc coating on iron and steel. Why? To just prevent rusting, or you can say that to give the long life to the metals like iron, steel. Okay. Next, you have to read is extraction of cast iron, or you say it as iron, because finally when it comes out of the furnace, it is cast iron. So concentration, the ore for this is what? Hematite ore. Okay. The hematite ore being oxide ore is concentrated by gravity separation process using hydraulic separator. Gravity separation process, we're using gravity, so you'll be having what? You'll have two pulley kind of thing. The thing will be going like this, the belt will be going like this. What will happen? Because of the gravity separation, the metal will form somewhere here and the impurities will fall somewhere here. Okay, the higher density, this will be how the different density will be there. So according to that separation, the higher particles will form here, fall here in this places, and the lighter particles will form here, and this will keep on moving in this direction. So because this is what is your hydraulic separator. The oxide is being heavier, settles to the bottom, while lighter impurities come out of the surface. So this will be more heavier. So here you'll get the oxide, and here you'll get the impurities. So because it is having oxygen, so we are doing calcination here. Sulfide, we are doing flotation. So the concentrated ore is heated in limited supply of Fe. So calcination, there what we were doing, roasting. Roasting is excess supply. Calcination is what? Limited supply. So what is the use here? Now whatever impurities like sulfur, phosphorus is present. Phosphorus is present in S4 form. They have been taken. So sulfur is being oxidized to SO2, and P4 is being oxidized to P2O5. If any carbonate is present, then it is dissociated to give oxide. If say, for example, iron is present, so FeO plus CO2. Okay, so this is how it is dissociated. Now next, after we are done with the calcination, thereafter roasting we did smelting. Here after calcination we'll do roasting. So the calcined ore is mixed with limestone, that is CaCO3, in a ratio, and the ore is in the ratio of 8:1:4. And charge, now what is this 8:1? What is present here at 8:1:4? So now we have CaCO3 here. So what is the ratio? 8:1:4. Okay. 8:1:4. So now ore in the ratio of 8:1:4. So I have taken the ore, that is oxide and CaCO3, and it is charged into the blast furnace. The blast furnace is cylindrical steel vessel, lined 6 meter. It is lined 6 meter in diameter. This is not important. So I'll not just, when you're reading it, you can read it. What is important? The ore is what? Hematite. What is we are doing? Why we are doing here calcination? We are doing because we have here what? Hematite ore. Hematite ore is iron. There it was, the ore is present, was sulfur was present at non-metal. Here oxide is present. So we are doing calcination. The difference between roasting and calcination. Roasting is excess supply of oxygen. Here limited supply of oxygen is there. Okay. We are doing here, there it was being separated for what? From forced flotation method. Here the concentration is done with the process of calcination. Okay. Oh, sorry, gravity separation. Now we have zone. We'll see in the next slide, the chamber is there. So the first zone, we have C plus CO2 plus heat, exothermic reaction. Here the temperature is maintained over 1500 degrees Celsius. Okay. Now, so what we'll see this reactions when we are seeing this thing. Red, what is red hot zone? I'll just take you to that slide where you can just see what is there. Okay, yeah. So this is, you can see from the reactions are written in the slides. Now what is there is the exhaust gases is coming out, the charge, ore, coke, and limestone. We have written the ratio 8:1:4. So charge, ore, coke. So what is there? Ore is there in the present. The ore is 8, coke in 1, and limestone and 4. So this is what is the ratios written there as 8:1:4. In this ratio we have applied it, and when we are trying to, the first it is forming what is in this reaction. This reactions is not visible to you here, but what is happening here is the same thing here. Whatever is happening, the same reaction we have written here. In this place we have written this. Fe2O3 is with CO, carbon monoxide, carbon. In the previous things we are using carbon for reducing agent. Here we are using carbon monoxide as reducing agent. Okay, so zone of reduction, where this we are trying to reduce it. So you can see that for the reducing agent, so they can ask you this as well, that what is the reducing agent when we are talking about extraction of iron? What is the reducing agent when I'm talking about sulfur, and when I'm talking about zinc, and I'm talking about copper? So there and all, the reducing agent we are using is carbon, that is coke. The form of this, that is coke. And this is which one? This is carbon monoxide. So this is what is being formed, and finally you can see that we are able to get iron. And the iron which is taken out from here is impure, and here it is known as cast iron or pig iron. In pure form, we are blisters, filter, all we have to remember. Okay, same whatever is there, you're supposed to remember all that. The impure forms, which is the what is the impure form name when you're talking about copper? What is the impure form you're talking about zinc? What is the impure form we are talking about iron? So here it is cast iron or pig iron. We'll just see later on that there is a difference when we are talking about wrought iron. This is a bit different when we are talking about. Next time only we have this. So cast iron and wrought iron have big differences. Cast iron is an alloy consisting of 2 to 4% of carbon, okay, with a trace amount of silicon, manganese, and other elements. It is called as cast iron because it is made through casting. Okay, it is used for metalworking companies smelt raw iron or pig iron. Once smelted, the molten iron is mixed with carbon and other alloys. This is not that that much stronger. Wrought iron, on the other hand, consists primarily of iron with. So how much more iron will be, how much more carbon will be there? No, that much brittle it will be. Brittle, you know, right? It will break when you're trying to convert it into different form. So this iron is smelted slag and created by byproduct. While the exact composition of iron slag varies, it typically consists of elements like silicon, phosphorus, and sulfur. Can we go through NCERT book for chemistry? For inorganic chemistry, you can go from for the textbook. For inorganic chemistry, yes. For organic, only NCERT will not be enough. For physical, also NCERT will not be enough. For inorganic section, yes, you can go. Next, so when I'm talking about this thing, so cast iron is easier to produce than wrought iron, which is its counterpart. But wrought iron is also stronger than cast iron. Cast iron is harder than its counterpart. That means from the wrought iron. So wrought iron is more stronger, but cast iron is harder. Which have more content of carbon, it will be more hard, but it will be hard means it will not resist, it will not try to resist. If you're trying to resist it, it will break. So that's why that is also a problem. So where more carbon content will be there, that will be more brittle. Types of steel is there. Types of steel, basically what is there? Carbon steel. Okay, it is, so you have to know what is, it's dull, mate like. Okay, it's known to be vulnerable to collision, sorry, corrosion. So obviously it is not good. It's also get corroded, it gets rusted easily. Okay, it's normally used as knives, high tension wires, and automotive parts, and some similar items. This is what is important for use. Alloy steel, most is stainless steel. The tool steel, the name only suggests that it is used as tool. Alloy is what? It's a mixture of several different metals like nickel, copper, aluminum. Tend to be more on the cheaper side, more resistance to corrosion, and are favored for the some car parts, pipelines, ship hulls, and mechanical processes. The strength depends on the concentration of element that it contains. Concentration of which one? Nickel, copper, depending. Normally, when you are putting nickel, it becomes more harder. If we're talking about aluminum, it becomes light, but it's still very exceptional behaviors. It is like I'm talking about pipeline, it doesn't get corroded. Aluminum is used more. Ship molds, aluminum used more. Nickel being costly is used less. Mechanical project, we're trying to use copper more in that, like say wiring and all. If you want something should not get corroded, so we increase the concentration of copper in that. So this is how we vary the concentration of these things. Now, when I'm talking about tool steel, it is hard and both heat and scrape resistant. Okay, they're made up of cobalt, molybdenum, and tungsten. You can see all this metal which is present in the carbon, everything is D block element. So it has durability and heat resistant feature. Okay, so carbon is worst, carbon steel. Alloy steel is better, depending on this. Tool steel is still better than that. Tool steel is normally when I'm talking about some tools like when you're talking about, you could tell grinders, cutters, all these things, we're trying to use tool steel. Next, stainless steel, shiny and generally has around 10 to 20% of chromium. Chromium have a tendency that from chromium you can get a very sharp edges. Steel is resistant to corrosion and very easily molded into various shapes. Stainless steel, we're talking about stainless steel. Because of their easy manipulation, flexibility, and quality, stainless steel can be found in surgical equipments, okay, home appliances, okay, silverware, and even implemented as exterior cladding for commercial industries and building. Claddings, if you see, they will make claddings literally like this for bigger buildings for their working. So, or if they're trying to do plastering work and all. So for that and all, that we use claddings. That is known as claddings, which is also used for stainless steel. But no one that much uses stainless steel still. All excuse me, in India, that much big companies are there, so many, but they all of them don't use stainless steel. It is basically depend on that area is how, but yeah, it can be used. But yeah, for most of the surgical equipment, obviously stainless steel. If you talk about some experimental equipments which is there in the laboratory and all that, steel is required, that also will be made of stainless. Most pure form, I'm writing now 10 to 20% of chromium. 10 to 22% of chromium is very good, and it makes it still costly also. That is not that much important slide. What is now next is manufacturing of steel. Two processes are there in this. The first one is by besmerization process. Okay. So in besmerization process, what is that? The impurities present in cast iron are removed by oxidation. So what we are doing is, see, we are taking carbon, sulfur, silicon, manganese, all this we are trying to convert it into the form where it can be taken out. So this all will be then, as you can see, manganese silicate is formed in the form of slag. If phosphorus is present, that is again will be taken out in this form. So that you should remember this. This is Ca3PO4 whole twice, which is known as calcium phosphor or Thomas slag. Okay. Or Thomas slag. This is, so you should know what is Thomas slag. Okay. If you are reading NCRT besmerization, or you can to understand the concept of roasting, calcination. If you're talking about iron, whatever, you can't find steel in that. You can't find. You will find source rotation is what. You'll find out gravity separation is what. But in depth of manufacturing of steel and all will not be there in that. Okay. I just realized when you said, and I was doing this. Okay, so now this is the thing which is what we are using here is this. It is kept in the decimal converter, which is what we are doing. What will happen? The carbon is oxidized to carbon monoxide, which burns with light blue flame. Okay, light blue flame. And the mouth of decimal converter, when the flame dies out, calculated amount of spilgicine is added. It's a mixture of chemical, and it's, no need to know that what is that mixture. Then the steel is manufactured. The process is completed in 15 to 20 minutes, and the batch size will be 500 to 600 kgs. The quality of steel obtained by besmerization process is not that uniform, so it's not that much good. The first process, okay. Next, so we have Siemens-Martin's process or open hearth process. This is what you're supposed to know when you're talking about manufacture of steel. More important. See, I'm giving you those things and I'm saying you important, and I'm put it also in the slides because to meet, I am just trying to give you a comparative study. You'll just study whatever is there, you're just sticking to that. It's not that much enough. So it's better so you just have a comparative study. Okay. So what happens here is, okay, we have CO2, that is what is producer gas. So what we are trying to say is we have carbon, we are trying to react with Fe2O3, we are getting, this is what we are trying to separate. Iron we are trying to say, we're saying cast iron you say. And if phosphorus is present, this is what we'll do. We already read this thing phosphate. This is a Thomas, this thing. So now what is there is in this, we have, so one is what producer gas is CON2, okay. This can be regeneration, which we'll be using. And again, the impurities lining of earth is acidic. Okay, because whatever non-metals normally metals form basic oxide, non-metal forms what acidic oxide. If phosphorus is absent, or basic lining if phosphorus is present. Okay, so if phosphorus is not there, so if this all is there, so what will be there? It will be acidic. If I have this plus phosphorus, then this will be basic lining. Okay, so you're supposed to know this, that's why I wrote this. Next, so mixture of cast iron, scrap iron, hematite, all these are lime is kept on the hearth of open hearth and furnace. Mixture is heated by heated. It is heated by burning producer gas U plus N2 by regenerative system. The outgoing earth gas is preheated. It's preheat the incoming producer gas. The outgoing earth gas will be preheating the incoming producer gas, which and combustion can generate higher temperature. The slag is formed, is removed, and small amount of steel is withdrawn from the earth, and it is analyzed. First, it is checked. The percent of carbon steel can be increased by adding spelaging and can be decreased by adding scrap iron. So it depends on the process is slow and takes 8 to 10 hours, and quality of steel is better as sample can be analyzed. Because in the react, while it is being formed, we can check it. There it was 15 to 20 minutes. Here you can say that is 8 to 10. But still, this is more uniform, more proper. It can be used for more better purpose. So that's why we try to use this thing as your process for performing the. Okay. So till now, whatever we were talking about was of non-metals. Sorry, of metals. Now we are going to read about is non-metals. Here now, if I am just generalizing what is there, you can also see a lot of theories there. If you've been reading chemistry, most of the time you'll feel chemistry is full of theory or it is full of exception. See, what is there is obviously because you try to study, there will be a lot of logics will be there in that. Every logic is not written in the textbook. Experimental data will be written and directly they'll be told because see, in 2 years you have to read a lot of things, so they can't tell you to just study chemistry. It needs a lot of time. Okay. Anyway, exams are near. You have anyway already have seen a lot of problems. You're seeing Wrought, so you have to tackle this for coming few days so that you can just finish up your exam to get into good colleges, and then further at least if you don't want, you don't have to touch chemistry. If you're doing engineering, you have to read that just for one semester as one subject, and that is not this much of in-depth theory. There will be a lot of physical chemistry. If everyone try to, or if anyone likes to solve questions, that will be there. So metals, whatever we read, whatever is important, mostly you can see this is basically roasting, calcination, sulfides or oxides or silicates, which is being formed. So there is very few questions come from that side when I'm talking about this chapter. More questions will come from this non-metals part, because now you'll be discussing about preparation of which one, group 15, group 16, group 17 elements. Like I'm talking about chlorine, or I'm talking about ammonia, which will be using nitrogen. If I'm talking about H2SO4, that will be using oxygen, sulfur, group 16. So we'll see that. So more questions will come from this side. That doesn't mean you just leave metal, but this will be what will be more important compared to metal and non-metal studies. This will be what will be more important. So it's better you have to keep that also in mind, that I have to give focus more to which section. Anyway, so everyone, you have to just see that. So non-metals, now starting with water. Water is basically, when I'm talking about water is H2O. When I'm talking about water is H2O. So a water can have a shape of what? Water can have a shape where we're talking about. So let's talk about water. Water structure will be, this is O, lone pair on this. And this I have hydrogen. So I have hydrogen. So this is how this is, because of the repulsion of lone pair present here. This will, instead of being linear, it have been bent shape. Now, when I'm talking about water, water is there in form of hard water. Water contains what? It contains high amount of calcium ions and magnesium ion. Okay. You have health benefit because more, but if more is dissolved, it goes to the formation of what? It is going to the formation of this thing. Stones and all. Temporary hardness is due to the presence of bicarbonate of calcium and magnesium. Bicarbonate is HCO3. So you have calcium and magnesium. Either you have calcium and magnesium. Okay. Fine. So here we are basically, so when I'm talking about permanent hardness, it is due to the presence of chlorides and sulfates. Okay. Here it is bicarbonates. Here we have chlorides and sulfates of calcium and magnesium. Here it can be removed by boiling, but here it cannot be removed by boiling. We'll read by which processes it can be done. It can be removed. So permanent hardness. Now soft water is treated water which does not contain a high level of minerals. It is not suitable for drinking. It is produced via ion exchanging using sodium resins. We'll see all that methods now. So first thing is how to remove the hardness. The causes is basically of the presence of, so what we are, because of presence of what, silicates and chloride. When I'm talking about a permanent hardness, for a temporary hardness is because of the bicarbonates. So now removal of hardness of water, temporary hardness, how we can remove? Only by boiling. So soluble bicarbonates are converted into insoluble carbonates, which are removed by filtration. So we just take, this is what, this is calcium bicarbonate, magnesium bicarbonate. This basically, this heat will come here, this heat. So it will form what? CaCO3. It forms what? CaCO3 plus H2O plus CO2. Now when I'm putting this sign, this is basically, this is removed in the form of precipitate. Okay, so now you get a water which doesn't contain this. Okay, by CLAT's method, so calcium hydroxide is CLAT's reagent. So calcium hydroxide, you try to react the CaHCO3, or you can do this for MgHCO3 also. Same reaction will happen. There will be no reaction change. It will form what? It will form 2MgCO3 plus this will be this, because exactly same valency, so there will be no variation like this. So removal of hardness, they can just directly ask you what temporary hardness will be removed by boiling. Okay. Next, to remove the permanent hardness, we have different method. We have first GAN's permitted method. Okay, in this method, sodium aluminum orthosilicate, which is known as permutate or zeolite. See, this is why I said this all is important, this part. Sodium aluminum orthosilicate, Si2O2. The formula is Na2Al2 Si2O8. So this is what is known as permutate. This is what is the reagent used, or this is also known as, this is like this zeolite. You can't say this is only zeolite. Zeolite have different formulas, but yeah, this is a form of zeolite. But the exact name for this is permutate. Okay, what we do is it is reacted with Ca2 plus, because it will be containing calcium, these things. So silicate, then this will get Na plus Cal2Si2 at XH2. This is how it will be separating, and this is what we'll be using for the water. What you're supposed to remember, the formula for, see, if you don't remember this K, this XH2 over K, this will be XH2. So if you're not remembering this, you have to remember the permutate formula. Permutate formula you're supposed to remember. Okay, next is Calgon's process. In Calgon's process, what is there? The name is sodium hexametaphosphate. Sodium hexametaphosphate. Okay, that is what is the name. This is known as Calgon. Okay, sodium hexametaphosphate. This is the hardness of water is removed by the adsorption of Ca2 plus and Mg2 plus ions. Again, what you have to remember? Calgon. Permitted here, Calgon. Now, ion exchange resin method. In this method, the permanent hardness of water is removed using resins. Ca2 plus and Mg2 plus ions are exchanged with Cl minus or SO4 2 minus ions with anion exchange resin, which is RNH2OH. Okay, so demineralized water is formed in this process. We say no demineralized without mineral. Then we first try to demineralize it, and you can see about different brands of water, the purified water, aqua water, all this thing. There'll be some big brands. You'll say that minerals are added to it, the extra minerals you add to it. So that also is there when we are talking about this thing. Okay. So what is important? Again, why I'm saying, because while you are reading theory, you'll not feel to read. What all is important? You should know the name of permutate. You should know the name and formula of Calgon. Okay, nitrogen cycle. What happens in nitrogen? What are nitrogen fixation bacteria? So the most important we have rhizomes. Or you have rhizomobium. Okay, so nitrogen fixing bacteria, this will not get into biology anyway. So nitrogen fixing bacteria, so what they do is from the atmosphere, they'll contain nitrogen. So we are talking about group 15 now, like talking about group 15 elements, non-metal, group 15, talking about nitrogen 2,5, 2,8,5 phosphorus, those group 15. Group 15 is what? Group 15 is basically known as what? These are known as what? Pnictogens. Pnictogens are what? It's normally known as, these are normally poisonous. So this is what is pnictogen. Okay. So what they do is nitrogen from the atmosphere, nitrogen fixation happens, nitrogen fixing bacteria, they'll take it from the atmosphere. This one, nitrogen fixing bacteria, they'll convert it into the form of NH3. You can see that from this will be what? This will be leguminous plants. We say them legumes. We talk about this when we'll have chana, rajma, all these things are legumes, leguminous plants. From the root of that nitrogen fixing bacteria, they'll try to collect the nitrogen, then it will be converted into the form of NH3. Okay, now you can have decomposers which are there, so you'll have extra materials of this, you'll have excreted material. So these decomposers will do what? They'll try, so they'll collect it from them, decompose it. In decomposition, what will happen? Ammonification will happen. Ammonification will give you ammonia, ammonium ion. So ammonification will give you ammonium ion. Ammonium ion will try to combine this NH3, nitrification will happen, which will give you NO2 minus. So they'll try to combine. Again, nitrification will happen, that will form NO3 minus. Assimilation is what? It is absorption of N2 in plants. This, so like this only now NO3 minus again will be collected by the plants also. Again, it will be collected by the bacteria also, and then the bacteria will again we will be releasing it into the atmosphere. Again, from the lightning also you can have nitrogen fixation. From lightning also you can have NO3 minus when we talk about acid rain concept. But again, very it's not important. So you have to know that group 15, pnictogen, nitrogen cycle, what is important? It is in the terms of legumes plant or leguminous plants. Rhizobium is a plant nitrogen fixing bacteria is the rhizomus, you say, or you just remember from the name anything starting from this. This all is what basically nitrogen fixing bacteria. Okay. So next is the group 15. The more important thing is ammonia is there, that is NH3. So ammonia, we have how to do laboratory preparation of ammonia. We have reactants. Reactants is what? Ammonium chloride, that is NH4Cl. NH4Cl with calcium hydroxide. It is a straight line in the ratio of 2:3 by weight. Okay, the weight is 2:3 by weight. Okay, so the reaction is NH4Cl, ammonium chloride, calcium hydroxide forms CaCl2, 2H2, NH3. This is laboratory preparation. We have an Haber's process. H2, N2 forms NH3. Okay. So properties of ammonia is what? Ammonia is very soluble in water, but it ionizes partially in water to form a weak alkali. Alkalis are what? Alkalis are water soluble bases. Water soluble bases are alkalis. Okay. This is chemical properties. There's a physical property, which is a colorless gas. It's less dense than air. It's an alkaline gas. It's pungent smell. It's very soluble in water. Ammonia being alkaline can undergo neutralization with acids to form ammonium salt. So ammonia can combine with acid to form ammonium salt. For example, ammonia is reacting with HCl to form NH4Cl. This is also used for detection of HCl. Okay, this is white fumes of ammonium chloride. This will be white in color. Okay. Ammonia solution can react with solutions of some metals, except it cannot react with Na+, K+ and C2. This is a very reactive. These are reactive metals. Reactive metals. Okay. Now you have, so for example, we have Mn+. It will react with N mole of OH- to form metal hydroxide. Whatever number is there here, that number will come on this. So ammonia solution can react with what? Solutions of some metals ion to form this. This is actually important because this is used as a test for HCl. So it will react with this, and then after reacting with this, it will be going in this fashion. It will form what? It will produce NH4Cl, which will be detected by white fumes. So white fumes is produced and you can detect that there is a presence of HCl. And for detection of HCl also this is used. Okay, next so we have next is nitric acid, HNO3. HNO3 is nitric acid, very strong oxidizing agent. HNO3, it's a very strong oxidizing agent. The oxygen released from this is used for bleaching purposes as well. It's have a very strong oxidizing nature. So in laboratory, what we do, approximately equal masses of nitrate salts such as sodium nitrate with 96% of sulfuric acid, and distilling this mixture at nitric acid boiling point is 83 degrees Celsius. So what we do is the reaction is sodium nitrite. Okay, so sodium, so NO2 where will be there, that is nitrite. Okay, and whenever I'm talking about NO3, that is nitrate. So we have what? So all is basics. So NaNO3 is sodium nitrate. You can find out nitrate as a say here we have nitrite. So when I'm talking about this thing, so we have NaNO3 sodium nitrate in presence of H2SO4. It is very much, you can say dilute, but it is not that much dilute, which is 96% sulfuric acid with only 4% diluted it is. Okay, because the reason is to displace NO3, it's not like you have to displace what you have to displace sodium. Sodium being a very reactive, you can use here KNO3 also in place of Na, K will be there. So here also the only thing will be there, K2SO4 will be there. Only that much change will be there because from the same group, this will give you the formation of HNO3, H2SO4, kings of acid. So this is what is being used. Okay. Now next is physical properties of nitric acid. Molecular weight 63.1. Okay. Or density is this much, boiling point is this much, melting point is this much. What is important is chemical properties of this. Okay, nitric acid is a very strong acid. It turns blue litmus to red. It's a very strong oxidizing agent as well. Nitric acid decomposes on standing to form brown nitrogen dioxide. This is okay. So you need to be, this also is used in the form of test. This is the reason why it becomes brownish over time, though fresh nitric acid is colorless. Okay, fresh nitric acid is colorless, but because if you leave it for a longer duration, like say 3 months, 6 months like that, so it will form nitrogen dioxide. It's brown in color. It's again it's not only for this, if it just pass through heat through that, it will get dissociated into NO2, O2 and H2O. This is also used as a test for detecting HNO3. Nitric acid liberates hydrogen gas with metals above hydrogen in the metal activity series. So magnesium, this is, so normally you should know, right? Normally with all the acid, when you're talking, you're reacting some metal with HCl or you're trying to react some metal with H2SO4, most of the metals, they'll liberate H2. HNO3, most of the metal they don't do. There are a few exceptions, that is magnesium and manganese. We should remember this as well. This is exception when I'm talking about nitric acid. Nitric acid separates hydrogen from using this thing. So this is basically what this is exceptions. You should know that manganese and magnesium, they both are being used to react with HNO3 to liberate hydrogen. Most of the metal they can't liberate because HNO3 is a very strong oxidizing agent. So being metals is very strong reducing agents. So the oxygen which is liberated from HNO3 is a very strong oxidizing, acts as a very strong oxidizing agent because of the presence of that oxygen. Because when you break it, no, it will break it in this fashion. HNO3, it will break it like this. It will break it into HNO2 and nascent oxygen. This nascent oxygen is what is used as reducing, what is used as oxidizing agent. It is also a very strong bleaching agent as well, oxygen. So group 15, you have to know about ammonia and nitric acid. This is small, this thing, this is basically what is, we had to remember obviously lab, but in the industrial area, it is the HNO3 is produced by Oswald's process, and ammonia is produced by what? This is produced by Haber's process. So I have just given you the flow chart here. We have to, from this where we are talking about 90% platinum is there and 10% rubidium is there. This is a converter which is there, NH3 plus dry air, that is O2 will be there. After it is passing to this, the product of this is NO. This NO is being cooled After that, this is passed here. Again, this is an oxidation chamber. So NO2 react with O2 to form 2NO2. This NO2 is again fed from here to this chamber. You can say this as combustion chamber. So heat is being then here. Water is being passed out so that the gases will cool down. And through water, you can calculate the nitric acid here, HNO3 from this part. And the hot gases will come out of this part. Okay. This is the absorption tower here. That is basically, you can say that it is 68% HNO3 is present than 32% water. So that much diluted it will be there in this. Okay, this is when I'm talking about an Oswald's process. And I'm talking about ammonia. What is there? H2 plus N2 is combining. We are trying to put it into the compressor at 20 megapascal, that is 10⁶. It is passing through this. Again, catalyst, we are at 700 Kelvin. We are using catalyst, iron dioxide and H2O. Here we'll be also using promoters. Promoters are those things which you basically activate the, or which will increase the activity of the catalyst. Like if we talk about, so here, let's see, first finish this, we have molybdenum. So molybdenum is the promoter here. Now we can have the catalyst also. You have positive catalyst and negative catalyst. So promoter, they don't care that they are positive catalyst or negative catalyst. Promoters, their work is what? To enhance the activity of the catalyst. If it is a negative catalyst, they'll enhance the negativity. Of positive catalyst, positivity. That is how it goes. So you'll get a mixture of N2 plus S2 plus NH3 here. Then in from, if it is passed through here, it will be liquid ammonia. And from this liquid ammonia, again, this is connected N2H2 through the pump. It is again passed through here. Because if you write this is a reversible process. We write it like this. This is a reversible process. If you try to balance this will be 2NH3, so this will be 3H2. This is basically Haber's process, 20 megapascal, 700 Kelvin. Catalyst is iron oxide. Again, iron oxide. Promoter is molybdenum here. Okay, so next we have to read about sulfur, group 16. Group 15 we read, group 15C. In general, if you talk about group 15, we read about what? We read about which one? Ammonia we read, and HNO3 we read. So ammonia, they asked you the laboratory preparation, you'll write that. Again, HNO3 laboratory preparation, that is one thing. Second thing, what you're supposed to know about this is the major, so this is Haber's process is used. And here, what is there? Oswald process is used. You should know all this. Again, nitrogen, that is you're supposed to know. So further moving to group 16. Group 16 is which one? Group 16, we have sulfur. So now group 16 is basically which one? It is the name for them is what? Chalcogens. Why chalcogens? Because they are ore forming thing. Now, when I'm talking about sulfur and compounds, in basic, first we just see other types of sulfur. We have rhombic sulfur and we have monoclinic sulfur, S8. The form will be, one will be rhomboid and other is needle-like. Color, one is translucent yellow and one is transparent amber. Okay, so this is important. It is dissolved in CS2. Yes. What is CS2? CS2 is an inorganic solvent. Like hydrogen, water is used as a solvent, that is a polar solvent. So inorganic solvent you say, or you can see this because this is sulfur is a non-polar thing. So inorganic thing, this is basically a non-polar solvent to dissolve which one? To dissolve non-polar solute. So sulfur is solute here to dissolve non-polar solutes like sulfur. We try to use inorganic solvent or non-polar solvent. So CS2 is best example with this. Stability temperature below 96 degrees Celsius, it will be stable. It's above 96 degrees Celsius. You cross 96, you convert it to monoclinic. Okay. How is the preparation? Evaporating mixture of powdered sulfur and CS2 at room temperature. Heating the rhombic sulfur above transition temperature and cooling. Above transition temperature is above 96 degrees Celsius. You heat rhombic sulfur and you cool it, you'll get monoclinic. Select again the compounds when I'm talking about H2S, hydrogen sulfide. So hydrogen sulfide, the laboratory preparation of hydrogen sulfide is hydrogen sulfide gas is prepared in the laboratory by treating iron sulfide with dilute H2SO4. Iron sulfide is being reacted with dilute H2SO4. It will form FeSO4 and H2S. So ferrous sulfates and H2S will be liberated in the gaseous form. What is its physical properties? It has weak intermolecular forces which is existing between H2S, and the boiling point and melting points are way lower than that of water. Okay, the boiling points of water and hydrogen sulfide are 100 degrees Celsius and minus 60 degrees Celsius respectively. Okay, this is what is the difference. Chemical properties of hydrogen sulfide. Hydrogen sulfide is heavier than air by a minute margin. A mixture of air and H2S can lead to an explosion. Okay, there's very less difference in there. Oxygen and hydrogen sulfide catch fire with blue flame to produce sulfur dioxide and water. Hydrogen sulfide serves as a reducing agent and mostly in the presence of the base that makes SH minus. In the presence of catalyst or higher temperature, sulfur dioxide reacts with hydrogen sulfide to produce water and elemental sulfur. Okay, so this is again I said theoretical data. Next thing we have to know about the again see everything we are taking two of this thing. Two particular materials have been taken or two particular compounds have been taken out from that group and we're trying to discuss them. The sulfur dioxide obviously SO2. Laboratory preparation of sulfur dioxide Na2SO3 sodium sulfide. SO4 2 minus is sulfate. This is sulfate. And SO3 2 minus is sulfite. So it is reacting with H2SO4 to form sodium sulfate, water, and sulfur dioxide. Properties of sulfur dioxide: it's a colorless gas with a rotten egg odor. It have a very bad smell. I don't know if you have seen the experiment. If this smell comes out, it's very difficult to be in the laboratory. It's highly soluble in water. Okay. It liquefies easily. Liquefies means it's converting it to liquid is quite easy. SO2 dissolves in water to form sulfurous acid, H2SO3. Okay, due to which it possesses an acidic character. So it forms an H2SO3. If you see about carbon, we write it as H2CO3. Okay, carbonic acid. Here it is H2SO3, sulfurous acid. It does not support combustion, or is it combustible? No, it doesn't burn also, it doesn't support also combustion. It's a strong oxidizing agent. Okay, normally non-metals are oxidizing agent and metals are what? Reducing agent. So this is an exception. You can see it acts as a reducing agent as well. Okay, so SO2 can act as an oxidizing agent and reducing agent as well. Questions you can expect again in this form. What you can expect the question as that they'll say, they'll give you both those things and they'll say like, yeah, this is one thing is there. Tell me this, which among the following can act as both oxide or strong, both as oxidizing agent and reducing agent. So it's a strong oxidizing agent, but it's okay reducing agent. It's not a very strong reducing agent. Okay. Next, we are supposed to read contact process or manufacture of sulfuric acid H2SO4. Okay, so SO2 is prepared by burning sulfur in presence of excess of air. We get SO2. SO2 is again further converted to SO3. What we are doing for that? We are taking sulfur dioxide and oxygen at a ratio of 1:1 at a temperature 400 degrees Celsius to 450 degrees Celsius at a pressure of 1 to 2 atm. In presence of V2O5, what is this? Vanadium pentoxide. Vanadium pentoxide. Pressure is 1 to 2 atm. In the presence of vanadium pentoxide, that is a catalyst. This reaction is irreversible in nature. I can go from here to it, here to so SO2 is converted to SO3. Preparation of concentrated sulfuric acid. Now H2SO4 plus SO3. I'm reacting SO4 to form what? This is oleum. After this, This oleum is again diluted. Hydrolysis of that gives you H2SO4. So what is the first made to react with concentrated sulfuric acid? Sulfur dioxide cannot dissolve in water directly. So as it leads to the formation of fog, the product obtained after this reaction is known as oleum. So SO3 is first being diluted here because it cannot be directly dissolved in water. So SO3 instead of being first dissolved in H2SO4, then it forms H2S2O7, that is oleum. Oleum is dissolved in water to get H2SO4. Okay. Conditions, everything 400 degrees Celsius, 1 to 2 ATM, all this is there. All this is conditional. We already read about which processes. We read about Haber's, Oswald's, and contact process. Okay. Haber's is for ammonia. Contact is for sulfuric acid. Oswald is for HNO3. If I'm talking about which one, if I'm talking about the metal oxides, it will be basic in nature. If I'm talking about non-metal oxides, it will be acidic in nature. There are few things which are giving you amphoteric things, which are example, we have zinc is there, aluminum is there, all this gives you amphoteric oxides. Amphoteric is basically those oxides which give you both the nature, basic nature and acidic nature as well. One thing which we just came across is which have a strong oxidizing agent and it's a okay reducing agent as well. It is your SO2, sulfur dioxide. Now, so chlorine. So before getting into chlorine, group 17 basically. Now, so if I'm talking about group 17 is what? Fluorine, chlorine, bromine, iodine. So when I'm talking about fluorine, chlorine, bromine, iodine, as we read, we know that this is 9, this 17, then 18 you add to it. So all this keeps on moving. Fluorine is the first thing. It is the most electronegative element. Group 17. Now, where it is put up, so chlorine is, when I'm talking about this thing, the name for them is what? This is halogens. Halogens are basically what? They're salt forming. Halogens are basically what? They are salt forming. So we're talking about halogens, they are salt forming. Group 17 is known as halogen. They're just placed before group 18, that is noble gas. So they have and there, if you talk about group 17 and group 18, there is a huge difference in their properties. Okay. So group 17 is what? Fluorine is there. If I'm talking, so chlorine is basically just one more. This thing is, if I'm talking about fluorine and chlorine, okay, there's something known as electron negativity. Okay, right? We have something known as electron affinity. Okay, electron affinity is there. That is the affinity. See, what is the difference between electron negativity and affinity is, when I'm talking about electron negativity, it is what? It is attracting shared pair of electron. If I'm talking about which one? If I'm talking about shared pair of electrons, when I'm talking about electron negativity. When I'm talking about electron affinity, it is basically what? Attracting or accepting. I'm not saying, I'll not say it as attracting, because this is not a process where we attract. This is accepting. The word correct will be accepting pair of electrons. Now, so this is a definition when I'm talking about electron affinity and electron negativity. Now we say what is fluorine is what? This is most electronegative. Fluorine is what? It is most electronegative. But when I'm talking about electron affinity, it is most electron affinity. This one will have. Now, why this? Now, the reason behind this is I'm writing the configuration for fluorine. I write fluorine configuration as 1s2, 2s2, 2p5. Now, when I'm talking for chlorine, if I'm writing, it will be 1s2, 2s2, 2p6, 3s2, 3p5. Now, if you see properly here, what is happening? In this case, is the number 1 shell filled, number 2 shell filled, number 3, okay, 3s and 3p is there. If you remember, if I'm getting into n equal to 3, so I can have L value as what? Up to n minus 1, so 0, 1, 2. Now 0 represents S, 1 represents P, 2 represents D. So if you see here, what is there? We have 3D0 here. It have a vacant orbitals here. So what is there in this is because it have place where it can accept the electrons and keep. Fluorine doesn't have fluorine. See, this is there. This is there. One more electron, it will be fed. So where will let us accept pair of electron? It can only have attraction. What it will do, it will try, because electrons are there in the form of clouds. What it will do, it will try to attract the. So here it will try to have, it will try to attract all the electrons. It will be more dense towards this side, and here it will start getting less electrons. So if here I'm keeping fluorine, if I'm keeping here some electron. So fluorine just try to attract the electron clouds towards itself. It cannot accept and keep it. So most electronegative, if I'm talking about it, is fluorine, correct? But if I'm talking about most electro affinity, we have to talk about what? Chlorine. So chlorine is that element which have most electron affinity. Fluorine is most electronegativity. Okay. Now, so we are talking about group 17. So in group 17, we have to talk about the first thing which we'll be reading is chlorine. So chlorine is what? Laboratory preparation of chlorine. What we do, we take MnO2, manganese dioxide, HCl forms Cl2, MnCl2, and 2H2O. Okay. Properties of chlorine, it is in a greenish yellow gas with a pungent and suffocating odor. It is soluble in H2O. We have the things now. You can see that it is with metals. If you're trying to react chlorine, it forms metal chlorides. Or if I'm trying to react with non-metals with chlorine, it will form what? Non-metals chloride. This is a general reaction. This is very important. Okay. Now what chlorine does it with dilute cold and dilute NaOH, it gives you NaCl, NaOH2, and even with Cl2, 6 NaOH, NaCl, NaOH, ClH2 it gives. But what is the difference here? I'm taking hot concentrated here, and if I'm trying to take cold dilute, what thing is different here is, see, I'm just increasing the number of moles over here. The reaction in this reaction is comparatively very fast compared to this one. This is what? Sodium oxychloride, NaOCl2. Now, when I'm talking about ammonia, if I'm taking ammonia in excess, I get NH4Cl. This is what? This will be white fume. White fuming gases will be present for this. White fuming gases. So this is NH3 plus Cl2 plus NH4Cl. NO2 will be liberated when I'm talking about excess NH3. But if I'm taking excess of chlorine, this is what? When I'm taking excess of ammonia. If I'm talking about taking excess of chlorine, it will form NCl3, that is nitrogen chloride. Okay. Which will liberate 3HCl. That's, though it is not used as a preparation of HCl, this is what HCl will be coming out from this extra product or byproduct. N2, this is byproduct. Now you have bleaching action. Bleaching action basically is oxidizing agent. So CaOH, which is calcium hydroxide or slate lime, with chlorine, it will form CaOCl2. This is what? Bleaching powder. Okay. This is bleaching powder and replaces calcium chloride and H2O. And this Cl2 with water, it will see this O. So this is all is what? This is nascent oxygen. This nascent oxygen is a thing which acts, which makes it to have a good bleaching agent as well. And this is a good oxidizing agent also because of this nature. Okay. So this is about chlorine. Next. We're talking about hydrogen. In hydrogen in the laboratory, it is prepared in this form. Okay, and have hydrogen in this laboratory is being prepared. Now this is the reaction. We have Na2CO4, Na2, NaCl, which is being reacted with H2SO4. And with this reaction, if you see further, we are trying to find out what is happening here is at 200 degree, this will be 200 degrees Celsius. The temperature will be 200 degrees Celsius, and this will form what? NaHSO4, HCl will be collected. This is hydrogen chloride. Correct. So now when I'm talking about this, so next physical properties of HCl will be hydrogen chloride is a colorless gas. It have a pungent smell. It's slightly sour in taste because HCl is there. Fumes in moisture. It's not combustible, just extinguishes. A glowing splint will be there, or very small. This thing will be there. We'll find out very small glow, like it will go for a second. Very soluble in water solution called hydrochloric acid. Okay, when you are mixing hydrogen chloride with water, boiling point is minus 83 degrees Celsius, freezing point is 113 degrees Celsius. Okay. When we are coming to chemical properties of this, aqueous solution of hydrogen chloride is acidic in nature and changes blue litmus to red. An aqueous solution reacts with metal oxides and hydroxide carbonates or bicarbonates to form corresponding chlorides. So HCl with calcium forms CaCl2, HCl with MgO forms MgCl2, HCl with NaOH forms NaCl, HCl with CaCO3 forms CaCl2, NaHCO3 Ca. Okay. It's corresponding chlorides only, they are forming everywhere. You can see it. This is what, this is metal, this is oxide of metal, this is hydroxide of metal, this is carbonate of metal, this is hydrogen carbonate or bicarbonate of, as you say hydrogen carbonate, you say it as, or you can say it as bicarbonate. Both is the same thing. Many books use this, but for most of the books they'll write both, or in the reaction they can say your hydrogen carbonate or they can say bicarbonate. This is very important for you, formation of Aqua Ratio. So formation of Aqua Ratio is basically what is mixture of 3 parts of concentrated HCl. It will be mixed with the chloride of, it is mixed with 1 part of concentrated HNO3. Okay, this is known as, so we say it as a mix, or we can say Aqua Ratio is what, HNO3 and HCl, which is taken in the ratio of 3:1. Okay, so this is very important. Why this is important? This, see, the nascent chloride released during the mixing can react with noble metals like gold, platinum to form metal chlorides. Because normally gold and all, they are unreactive. Gold, platinum, all this thing are like, they are non-reactive metals because they are very low in when we are talking about the activity series. So because of this, what happens? They are considered to be what? They are considered to be having very much unreactive. Very much unreactive. So when we are talking about they are very much unreactive, I need something to combine with gold and platinum. So we have this thing, the nascent oxygen, nascent chlorine, which is taken out. Nascent one basically is used for, like, it is immediately formed. And if you're not using it, it can get, it is very reactive. It will combine with something to form a particular compound related to what it is combining. So it is very reactive. So this is what is there, and this because it have very reactive, or it is very reactive, it combines with gold and platinum. Okay. So in general, diluted HCl does not react with nitrates, but can react with silver nitrate to form white precipitate of silver chloride. So HCl is normally not reacting with HNO3, but it can also does what is HCl plus HNO3. It can combine with HNO3 to give this. Okay. What is important here is your Aqua Ratio, which is what, combining of HCl and HNO3 in the ratio of 3:1. Okay, now see, we have a very small topic which is there when we are talking about the valencies of the different elements, which I think most of you will be knowing as well. But as a bit, you can just think that if I'm talking about univalent valency, like say if I have ammonia is there, it's just one, then we have Au plus, then we have Cu plus, then we have H plus, then we have Hg plus, then we have K plus, then we have Na plus, then we have Ag plus, then we have lithium plus. So this you can see, I am writing why this all are univalent, or we say it as monovalent. Name for all this, if I want to write the name for all this, this is what, this is ammonium. This is what, because the Latin name for gold is what, aurum. So because in aurum again we have the we'll see that when we're going to, it is trivalent as well. So because this is +1, it is known as Aurus. We have copper. For copper again we have name for this is cuprous. +1 oxidation, so cuprous. Hydrogen, H plus, it is hydrogen only. If it is H minus, we write it as hydride, but in plus we write it as hydrogen. Hg plus is what, mercury. So we write it as mercury because He plus 2 also exists. So the smaller one will be written as mercurous. K plus is there, potassium. So your potassium will stay as potassium. Sodium as sodium. Okay. If you represent the name of potassium, we write it as kalium. The name for this is what this is, kalium, the Latin name. And when I'm talking about sodium's Latin name will be what? It is natrium. Okay. Ag plus is what? Ag plus is argentus, because silver, the Latin name is what? Argentum. So the name here will be what? Argentus. Lithium will stay as lithium. These are few examples when I'm talking about which one. I'm talking about monovalent thing. Okay. If you are, it's possible you can take a screenshot. If you're writing, it is good. Okay, this and all is important for you because while writing the names, you'll get confused because you have to write the reactions. So then while you're writing the reactions, you should know that what to combine with which one. This all are positive ions. Okay, this all are positive ions. Okay. This all were monovalent. Now, if I'm talking about divalent, so we have Ag2 plus. We have Ba2 plus. This all are commonly used. I'm giving you Ba2 plus. Ca2 plus is there. Then we have Cu2 plus. This all are divalent. First was monovalent. Then now we have Fe2 plus. Then we have Mg2 plus. We have Hg2 plus. We have this is Hg2 plus. We have again a Pb2 plus. Pb2 plus. Sn2 plus. Zn2 plus. Platinum 2 plus. Nickel 2 plus. So Ag2 plus, the first one, it is plus 1 is argentus. Then I'm talking about plus 2 is argentic. The bigger one will end with ic. So argentic. I'm talking about Ba2 plus. Ba2 plus doesn't have any name. It will stay as barium. Calcium will stay as calcium. Copper, here again we have already written the cuprous. The bigger one is written as cupric. So because the name for this is what? Copper, so cupric. Fe2 plus, first one is it's less, 3 plus will come here. So lesser one will end with us. So ferrous, the Latin name of iron is ferrum. This is magnesium. Hg2 plus, Hg plus was mercurous. This will be mercuric. Bigger one will end with ic, mercuric. Plumbum, so because it is small, it will come to plus 4. So this will be what? Plumbus. The lead Latin name is plumbum. Sn2 plus is there. Sn2 plus is, we are talking about tin. So tin in plus 2 state is known as stannous. Zinc is taken as zinc. Platinum will be taken as platinus. Platinus. Nickel as nickel. This all is your after monovalent. This all is divalent. We'll write trivalent, tetravalent. Then we'll see the negative ions. Okay. So this is there. This is divalent. Okay. Next, when I'm talking about trivalent, we have Al3 plus. We have Fe3 plus. We have Cr3 plus. We have Au3 plus. Au3 plus. And then we have Bi3 plus. Then we have As3 plus. Then we have the tetravalent. We don't have much. We have Pb4 plus. We have Sn4 plus. We have Pt4 plus. So what are the aluminium will stay as aluminium. Bigger iron valency ferric. Chromium will stay as chromium. Iron, this is again gold. So smaller one was Aurus, bigger one auric. bismuth, and this is what is arsenic. Talking about lead, Pb4 plus, lead is what? Bigger one, plumbic. Plumbic is there. This is what? This will be stannic. And this is what is platinic. Okay, so this is when I'm talking about the positive ions, when I'm talking about cation thing. Okay, so cations, when I'm talking about, this all is there. Okay, so we'll just see the negative and acidic radicals. Positive is also named as, you say it as cations, or you say it as basic radicals. When I'm talking about negative radicals, we'll just see negative radicals. So negative radicals, if I'm talking about monovalent, I have CH3. So I'm just giving you the most common ones where you can just write down which things is required for your inorganic. HCO3 minus, HS minus, HSO4 minus, HSO4 minus, HSO3 minus, Br minus, or instead of writing Br minus, you can write it as X minus. Everything will come in that. X minus, MnO4 minus, okay, O hydride H minus, and OH minus, Cn minus, NO3 minus, NO2 minus, ClO2 minus, ClO2 minus, ClO minus, ClO3 minus, ClO4 minus, and last one AlO2 minus. You'll find out several names related to all this. That's why I'm telling you to note it down. It will be helpful for you later. This is what? This is acetate. This is acetate. This is known as bicarbonate. You say it as bicarbonate, or you say it as hydrogen carbonate. This is bicarbonate. HS minus, if you're right, this is bisulfide, or you say it as hydrogen sulfide. So bisulfide. HSO4 minus is bisulfate, or you say it as sulfate. This is hydrogen sulfate, or you say it as bisulfate. HSO3 minus is bisulfite. X minus is basically for Br minus, Cl minus, and F minus. You write it as halide depending on Br minus of bromide. So we write it as halide. Okay. MnO4 minus is there. MnO4 minus, we can write it as permanganate. Permanganate. This is hydride. OH minus is hydroxide. Cn minus is cyanide. Nitrate. Nitrite. ClO2 minus is chlorite. So this is minus here. This is basically, this is minus, ClO2 minus, yellow minus. This is chlorate. ClO2 minus is chlorite. ClO minus will be your hypochlorite. ClO3 minus will be your chlorate. ClO4 minus will be your perchlorate. ClO2 minus will be your meta-aluminate. Okay. So this all is a monovalent. Okay. monovalent negative ions. But then I'm talking about divalent. So we'll have, this is what, this is carbonate. This is common. This is dichromate, Cr2O7 2 minus. We have oxide. We'll just write the, I am writing the name. We'll just write the formula for this. Oxide is O2 minus, peroxide is O2 2 minus. The next one is your sulfate. Sulfate is SO4 2 minus, sulfite is SO3 2 minus. Sulfide is there S2 minus. Silicate is there SiO3 2 minus. Thiosulfate is there St S2O3 2 minus. ZnO2 2 minus. PbO2 2 minus. SnO3 2 minus. And I'll write more here. MnO4 2 minus. CrO4 2 minus. COO 2 minus. So all this I'm trying to write. So what will be the name? CO3 2 minus is what? This will be carbonate, dichromate, oxide, peroxide, sulfate, sulfite, sulfide, sulfide, this is sulfide. Okay. SiO3 silicate, StO3 2 minus thiosulfate, zincate, plumbate, okay, zincate, plumbite, then this will be stannate. MnO4 2 minus will be manganate. CrO4 2 minus will be chromate. And this will be what? Oxalate. CO2 minus will be oxalate. It's always divalent negative thing. Just write down trivalent and tetravalent. So if you have trivalent, you can write it as ASO4 3 minus, ASO4 3 minus, and 3 minus is nitrite. ASO 3 minus is there. One is arsenate, arsenite. P3 minus phosphide. PO4 3 minus. PO3 3 minus. BO3 3 minus. ALO3 3 minus. C4 minus, and FeCN whole 6 4 minus. Name for this is arsenate, nitride, arsenate, nitride, arsenite, phosphide. This is phosphate, phosphite, BO3 2 minus, this will be 3 minus will be borate, this will be aluminate, C4 minus will be carbide, FeCN4, so whole 6, this will be ferrocyanide. This is almost covers your inorganic 80% of things. One complex compounds will be there, which is not there for you to, so much of this thing is not needed. But as a basics, you should know all this. Okay, fine. So this is what was there for the in the terms of valencies, which you're supposed to know in terms of valencies. Okay. So if this is there, this is what you're supposed to know in the terms of valencies. Now, if we're talking about inorganic, we have read everything. We have read about the metallurgy part. We have read about everything. Okay. So this is basically what is your what we have and present when we are talking about inorganic chemistry. See, inorganic chemistry, we have already talked about atomic structure, periodicity, valency, which was there. I have told you this. Most commonly, you will be knowing all these valencies. You will be writing the names as well. Just to brush up, you have just written this. About which I wrote today, wherever you find out the conditions like temperature, pressure, reaction part, all that you're supposed to know. Now, which is their raw form where they're supposed to be converted from this, like we're talking about cast iron or pig iron, or strong in terms of sulfur in terms of zinc. So all those things where you are finding, there will be certain in pure format will be there, and that is supposed to be converted into pure form. You are supposed to know all that. You are supposed to know the reactions. When it comes to the reactions of your laboratory preparation for H2SO, SO2, HNO3, all this thing is supposed to be required. Process are which one? Haber's process, Oswald process, contact process. It's there. Write the reaction of which you are supposed to find out which is this reaction where which justifies the oxidizing nature of chlorine or oxidizing nature of when I'm talking about like when it is reacting with chlorine is reacting with something, how you're supposed to find out its oxidizing nature, or if they can ask you why the bleaching nature of the or which reaction among this justifies the bleaching nature of chlorine. So all this thing they'll not give you directly like this reactions you have to write. So you have to know the reaction which is justifying all this. So everything whatever we have done today contains almost everything, like whatever inorganic we have done. Next we are moving into organic. So your physical part, inorganic part is done. If you have some questions, you can try it out. We have been trying, I have tried to solve few questions in the class. As we are finishing all these things, again we'll have revision sessions as well. So keep on starting, everyone. Okay, we are done with the inorganic sections and physical. Next we are doing organic for our next chemistry class. Okay. Anyway, thanks for today. Bye, everyone.